Okay, welcome to number 2 in the series of series circuits and how to analyze them. In this case, we're going to apply Ohm's law and the basic idea that the resistance in a series circuit is simply the sum of all the individual resistances to calculate the total resistance and the total current of each of these circuits. One thing that you might want to do is look at Ohm's law. Now, Ohm's law is essentially the definition of Ohm's law is that the resistance in ohms of any device or even circuit is defined as the potential difference, delta V, divided by the ratio of the potential difference, delta V, to the current, I. Again, I is the symbol for current, in amperes. So we're going to take delta V divided by I if we're trying to calculate the resistance. Setting it up in this little triangle just makes a quick shortcut for doing the algebra when you're trying to solve Ohm's law. Okay, so in this first circuit, the electrons would start here at the negative potential at the negative terminal with maximum potential. That means they'd have 12 volts. By the time they get back here to the positive, they'd be down to 0 volts, meaning the potential difference across the entire circuit is 12 volts. In terms of the total resistance, 2 plus 2 plus 2, all we have to do is add them together. That's a 6, and again the symbol is the Greek letter omega, so that's ohms. To calculate this I, if I go over the triangle, I is going to be delta V over R. And the potential difference between the positive and negative terminals of the circuit is 12 volts, so this is delta V. So 12 divided by 6 gives us 2 amps. And it doesn't matter what point in the circuit I take a look at, because there's only one pathway in a series circuit, we will have 2 amps at every spot. Okay, we go over this one. The delta V, the change in potential, the potential difference between the positive and negative is 6 volts. And the total resistance is 2 plus 4 plus 6. That makes 12. So we have a delta, so 12 ohms is the resistance. Just add those resistance values together. And then the current flow will be, the total current flow will be delta V, the potential difference, divided by the resistance. In this case, that's 6 divided by 12 gives us half of an ampere. Current's measured in amps. Potential difference is measured in volts, and resistance is measured in ohms. Okay, and this next circuit down here, it's again marked circuit A. I just kind of took several circuits and put them together on this paper. This time the numbers are bigger. We have 120 as our delta V, and they actually tell us that's our delta V. And we have 30 and 30 makes a total of 60 ohms. But it's a lot like the upper one where it was 12 divided by 6. Here it's going to be 120 volts of potential difference divided by 60, which still gets us 2 amps. And again, that would be 2 amps anywhere that we tried to put an ammeter on the circuit. It's a series circuit. The current would be the same everywhere. The next one, now this is slightly different in that we don't know this value of resistance, but we do know that the current is 2 amps. Okay, now the total potential difference is 24, so our delta V is 24. And then our current in the circuit everywhere is 2 amps. That means our total resistance, so we're over here in the triangle, R, is going to be the potential difference 24 divided by the current 2. So 24 divided by 2 is 12 ohms. And we know already this has to be 2 amps because if it's measured anywhere in a series circuit to be 2 amps, it's 2 amps everywhere. That allows us to figure out this final total resistance here. And that value is going to be, see, we need 12, we have 2 and 4, so we need another 6 to make that complete. Okay, so the green line just separates the two different circuits from above from the others, just to make it clear. So now in this one, we're kind of back in the same boat we had last time. We do have the current traveling in the circuit. Now again, it's series, so it's the same everywhere. So this is 2.4 amps. When we look for the resistance, again, it's going to be the R. The resistance is defined as the delta V, the potential difference, divided by the current in amps. 24 divided by 2.4, and that's going to bring us 10 ohms of total resistance. Now, so far we have 2, and we have 2 more is 4. Well, that means this one has to be 6. Oh, sorry, nope, missed the 4 over here. So 2 plus 4 is 6, plus 2 more is 8. We're down to only 2 in this one. So again, you can always check yourself. One of the nice things about electric circuits, you could always check yourself. Just go back and add them everything up. It's 2 plus 2 is 4, plus 4 is 8, plus 2 more is 10. And it should match your total resistance value. And we can put a big check mark next to that. Okay, so for the circuit over here, circuit D, we're looking at, this time we don't know the potential difference, but we can calculate the total amount of resistance. 2 plus 2 plus 2 for the 3 light bulbs is a total of 6 ohms. And the current is 3 amps here in this particular ammeter, but that means it's 3 amps everywhere. So the total current is 3 amps. Now we want to calculate delta V. So from our triangle, delta V is actually on top. So that means we're going to want to multiply the other two quantities. So 6 times 3 is going to give us a total potential difference between the positive and the negative terminal of 18 volts. And that's it. So that's how you would analyze a series circuit. A couple of other ideas to finish up. The idea of a ratio is very powerful when you're working with circuits. The resistance and current ratios are simply going to be the inverse, typically, of each other. So in this first circuit, we have just one 2 ohm resistor across 12 volts of potential difference. In the second one, we have two 2 ohm resistors. We have 2 times the resistance compared to the first one. That means in the circuit, we're going to have half as much current. The two are inversely related to each other, and it's just going to be a simple ratio as to how that changes. So the equivalent resistance of circuit X would be less than, it would be 1/2 of circuit Y. The current in battery X therefore would be greater than, it would be in this case 2 times more. So the ratio of current flowing in circuit X to circuit Y would be 2 times more, and the circuit with half as much resistance will always get 2 times the amount of current. Okay, now that ratio will be true for any series circuit with the same overall potential difference. So if we had a circuit where we added another 2 ohm resistor and we had 3 times more resistance, then that circuit would have 1/3 as much current, or a circuit with 4 times as much resistance would have 1/4 as much current, etc., etc. So it's just really a simple ratio. Sometimes instead of looking at the equations, it's easier just to think in terms of the overall ratios. Okay, so last and number 8, we have light bulbs that are all the same. If we have a circuit that has 3 light bulbs to a circuit that has 2 light bulbs, we want to try to figure out which one's going to have more power. And I got to be careful about this one. This is counterintuitive. Power is a measure of the change of energy in a period of time. If you go back to all the different power equations, we're hooking the same circuit up. We assume that all the light bulbs are identical and that the potential difference is identical, so the resistance of the one with 3 light bulbs will be greater. If we look at the power in terms of what happens with resistance, we can use delta V squared over R and do a comparison with that. Now, for a given potential difference that is set, if we decrease the resistance, then that means the power is going to go up. So in this case, it's actually the circuit with 2 bulbs which will use more power. In a series circuit, more bulbs, more resistance means less current, which means less power. Yeah, so as you go and add more and more resistance, you would think, well, I'm adding more stuff, so shouldn't I be using more energy? No, the energy gets distributed between all those things, and you end up with actually using less energy. And that's why if you keep attaching more and more light bulbs, you're going to see them get dimmer and dimmer and dimmer. That is not very efficient, so it's a bad way to hook up things in everyday life. So typically, almost everything we use that is electrical is not hooked up in series, but is hooked up in some kind of parallel combination. Okay, so again, that last question is very counterintuitive. Be careful with that. Most people want to think, I've got more light bulbs, it must have more power. That's not true in series, it's only true in parallel. Okay, that's it for series. We'll look at parallel circuits next.